Welcome to the first part of our lesson on data manipulation. Today we will focus on cleaning, filtering, and transforming scientific data using Python. By the end of this lecture, you will understand why raw scientific data must be processed before analysis. We will walk through inspecting tables, handling missing values, filtering rows based on physical conditions, and computing derived quantities. Data manipulation is a fundamental skill in physics. Scientific data is rarely perfect when first collected. Sensors spike, units vary, and simulations output messy comments. Writing a script to clean your data ensures your analysis is both transparent and reproducible. Let us define some key terminology. Raw data is what you initially collect. Cleaned data has missing or suspicious values handled. Processed data has been filtered or transformed, and derived quantities are new variables calculated from the existing ones. Validating all of this ensures we preserve the physical meaning. We will use standard Python tools for this work. NumPy will handle our mathematical operations, Pandas will organize our data into tables, and matplotlib will provide the visualizations. We begin by importing these libraries and setting a random seed. For our first worked example, imagine a simple motion experiment that records time, position, and temperature. We define the raw data as a text string here and use pandas to load it directly into a data frame. This is the resulting raw table. A quick glance reveals a missing position value at 2.5 seconds and a suspicious temperature reading of 99 degrees Celsius at 3.5 seconds. Before analyzing the data, we must inspect it programmatically. We need to know the shape of the table, the data types, and where the missing values are. We use standard pandas methods to extract this information. The output tells us we have 10 rows and 4 columns. The data types are correctly recognized as floats, and the system confirms exactly one missing value in the position column. Next, we generate summary statistics. Calling the describe method on our numeric columns provides a quick overview of the mean, standard deviation, and the minimum and maximum values. Looking at the statistics output, the temperature column immediately stands out. The maximum temperature is 99 degrees, while the median sits around 25.5. A temperature of 99 degrees is highly suspicious for a short, room temperature experiment. However, we do not want to silently delete it. The better scientific practice is to flag it for exclusion while keeping the raw record intact. Now we clean the data. We create a copy of the raw data frame, explicitly flag any temperatures outside the range of 20 to 35 degrees, and then drop the row where the position was not recorded so we can safely calculate velocity later. Our cleaned data frame now includes a Boolean column called temperature_flag. You can see it correctly marks the spike at 3.5 seconds as true. To verify our cleaning logic, we write a quick print statement to isolate and display only the rows where the temperature flag was triggered. The output confirms that exactly one row was flagged as having a suspicious temperature. And here is that specific row. The spike occurred at 3.5 seconds, matching the sensor error we identified during our initial visual inspection. Filtering is about selecting rows that satisfy a specific scientific goal. Here, we restrict our analysis to the time interval between 1 and 4.5 seconds, and we explicitly exclude any rows where the temperature flag is true. This yields our filtered data frame. It is smaller than the original table, but it is now perfectly suited for analyzing the object's motion without being skewed by invalid sensor data. It is important to remember that filtering is a scientific decision, not just a programming command. You must always be able to justify why certain data points were excluded from your final analysis. We can now calculate derived quantities. Using NumPy's gradient function, we estimate the velocity from the position and time columns. We then calculate the kinetic energy per unit mass by squaring the velocity and halving it. Our data frame now contains these two derived columns. We can easily track how the velocity and kinetic energy evolve over the course of the filtered time interval. Visualization is a crucial validation step. This code prepares a plot of our filtered position data against time, allowing us to visually inspect the motion. Looking at the position plot, the curve slopes upward nonlinearly. This increasing slope is a classic indicator that the object is accelerating rather than moving at a constant speed. To confirm this, we plot our derived velocity against time. We use markers to represent the discrete estimated points calculated by the numerical gradient. The velocity plot clearly shows an upward trend over time. This confirms our physical intuition from the position graph that the object is undergoing accelerated motion. Visualizing both position and velocity gives us confidence that our data is clean and our derived quantities make sense. Only after this validation should we attempt any serious curve fitting or parameter extraction. While Pandas is great for labeled data, sometimes numerical solvers require plain arrays. We can easily extract our time, position, and velocity columns into a pure NumPy array using the _NumPy method. The resulting NumPy array strips away the column names and indices. It is highly efficient for pure math, but you must remember that column 0 is time, column 1 is position, and column 2 is velocity. This highlights a key difference in scientific computing. NumPy arrays rely on strict column positioning, whereas Pandas data frames preserve the metadata and physical meaning through explicit column names. Let us move to a second example involving simulation data. We use NumPy to generate synthetic time series data for a simulation step, alongside temperature, potential energy, and kinetic energy, merging them into a new data frame. This table mimics the output of a molecular dynamics log. We have thermodynamic properties recorded every 100 simulation steps. Simulations often start with a transient phase before reaching equilibrium. We apply a time step filter to isolate the stable data, selecting only the rows where the simulation step is 400 or greater. The output shows we successfully filtered the data. We started with 13 rows and trimmed away the first 4 transient steps, leaving us with 9 equilibrated rows. Our equilibrated data frame now begins cleanly at step 400. We can proceed with thermodynamic analysis, knowing the initial startup fluctuations have been removed. To visualize the effect of our filtering, we write a script to plot the full raw temperature data overlaid with the filtered equilibrated data on the same axes. In the plot, the blue circles represent the entire data set, showing a sharp initial rise. The orange dashed line highlights our filtered subset, confirming we successfully isolated the data after the initial heating phase. Next, we explore the relationship between state variables. This code prepares a scatter plot of potential energy versus temperature for our equilibrated data. The scatter plot provides a quick visual diagnostic of the physical states sampled during the simulation. Checking these relationships helps ensure the simulation behaved thermodynamically as expected. When building automated analysis scripts, you should include data quality checks. Here we define a function that verifies the presence of required physical columns before the script attempts to use them. The function runs and confirms all required columns are present. If a column had been missing due to a corrupted log file, the script would have safely raised an error instead of failing silently later. We define another validation function to summarize the data size, count missing values, and print the physical ranges of temperature and potential energy. The diagnostic output shows no missing values and confirms the temperature remains between 281 and 318 Kelvin, which is perfectly reasonable for this simulated system. After processing, it is essential to save your work reproducibly. This code exports our equilibrated data frame to a CSV file and immediately reads it back in to verify the operation. The output confirms the processed data was successfully saved to a local CSV file in our working directory. Reading the file back into Pandas proves that the column structure and numerical values are fully preserved, allowing us to share the cleaned dataset with collaborators. Let us apply these concepts. We filter our equilibrated data to find only the physical states where the temperature exceeds 305 Kelvin, and then we calculate the mean potential energy of those states. The output tells us that exactly 5 rows met this high-temperature condition, and their average potential energy is roughly negative 1488 electron volts. This is the isolated data frame of those hot states. It is a perfect example of filtering data based on a physical condition rather than just a time interval. Finally, we want to check for energy conservation. We plot the total energy against the simulation step for our equilibrated dataset. The plot shows that the total energy drifts slightly downward over time. In a real simulation, analyzing this drift is a critical diagnostic step to ensure the integrator is stable. To summarize our practice, remember that filtering by time step isolates a specific phase of an experiment, while filtering by temperature isolates specific physical conditions. Both are valid, but they serve different scientific purposes. We have established a strong workflow today: inspecting, cleaning, filtering, transforming, and validating raw data. In Part 2, we will apply these exact principles to parse more complex, structured scientific text files.